Yesterday we started learning about functions, and today we're going to expand on that a little bit more. The most important thing we learned yesterday were the terms domain and range. And in particular, we figured out that domain was all the x's that made sense to plug into a function, and the range was all the y's that actually were used in that function. When we learned about domain and range, you learned how to answer questions like what you see here, where it says, what is the domain of each of these functions? And you need to think, could you plug in all the possible numbers into these formulas, or is there anything that it would not make sense to plug in? On this first one, for instance, I know for a fact that you can't have 0 on the bottom of a fraction. So x can't be anything that would make the bottom 0. That means it can't be 2, and it can't be -3. That's why the book would write the answer on this as -infinity to -3, -3 to 2, and 2 to infinity. On the other hand, you could take the absolute value of absolutely any number at all. So all real numbers would work in this formula, and the answer would be -infinity to infinity. And the key to the last problem is that you can't have a negative number under a square root. So I know that 2x minus 5 has got to be greater than or equal to 0, which means that we've got to have x greater than or equal to 5/2. Here's a couple of questions that ask us what the range is. And again, when you're trying to find the range, what you want to do is think, what sort of answers could you get? What could be the possible values of y? You might notice I left off the first of them. That's because it's a little bit harder on that one, but we're going to look at these two quickly. So what's important with this first problem is that absolute value can never be negative. The smallest answer you can ever get for an absolute value is 0. And if I add 5 onto that, that means the smallest answer for this function will always be 5. I could get 5, I could get any number bigger than that, but I can never get anything less than 5. So 5 to infinity is the answer. And when you take a square root, unless there's like a minus sign out in front, the square root always ends up positive. You're never going to get a negative answer. You could get 0, but you can't get anything negative. That's why my range, the answers we could get, will be everything from 0 onward, but nothing negative. Now that's the quick review of the most important stuff that we learned yesterday. Today we're going to go on and talk about some more stuff involving domain and range, and then a couple of other terms. Well, what we were doing yesterday was looking at the formula itself and using algebra to try and figure out what the domain and range are. Very often, you'll instead be asked to look at graphs and answer those same questions. And again, the key thing is domain just means what are the x's that are in use, and range is all the y's. So if you're looking at a problem like this, you want to think, looking at where that graph is, what are the x's that are actually used here for the domain? Well, I don't see anything over at the left. Looks like this starts at about -3. And then it goes through -2, -1, 0, 1, 2, 3. It continues over to the right side of where this graph cuts off. And we can always assume on graphs that they're going to keep on going, which is why for this one, I would probably say that the range is from -3 to infinity. Now the reason I put probably here is that I don't know for sure what's happening exactly at -3. And it might be that this is actually an open interval where I'd put parentheses there, but looks to me like, yeah, it starts at -3 and then it just keeps on going. For the range, I basically do the same thing, except this time I'm going to look at the y's instead of the x's. And on this graph, it looks like there are no negative numbers that are ever used on the graph, but it looks like it starts at the x-axis and keeps on going upward. That's why what we would probably put here is 0 to infinity. Now again, I'm not positive if that's going to be an open or a closed interval, but yeah, it looks like 0 to infinity. Here's another graph where we're trying to figure out the domain, which would be all of the x's that are used, and the range. So look at that for a minute, see if you can figure that out. So going from left to right, this graph does not appear to have any negative x values at all. So it's like it starts at the origin. It starts at 0. And there's also what last year in trig class we called an asymptote, where it's totally undefined when x is 5. And that's why we would go from 0 to 5, skip over 5, and then go from 5 to infinity for the domain. When we find the range, what we're looking at is what are the y's that are used. Well, I can tell from the first part of that graph that all the negative numbers are all used. And on the second part, so are basically all the positives. It cuts off at the end of this screen, but it's going to continue to go down and probably get closer and closer to the x-axis. Again, it's not totally clear whether it's actually touching the origin, but if it does, we would also include 0, and it would be all real numbers, negative infinity to infinity, going up and down, that would eventually be in the range. When I was going through these in class, some people were saying, what's this negative 10, 10 by negative 4, 4? And all they're doing there is telling you the size of the window you're looking at, that basically each of those slashes is standing for 1, so like going up and down, you're seeing the part that goes from negative 4 to 4. But again, you can assume that shapes continue forever. So on this one, sooner or later, you're going to cover all the possible x's on the left and on the right, and that's why the domain would be negative infinity to infinity. On the other hand, the range, you never have any negative values of y. The bottom of it is at the origin, so that's why we go from 0 to infinity. There are a few other terms that in your book they make a big deal out of with functions that I want to mention to you and make sure you get hopefully the main idea of them. The next one's what's called continuity, or being continuous. And what it means to be continuous is basically the function just keeps right on going. It doesn't stop for any reason. In the graphs you're looking at here, the one that's at the bottom left is a continuous function everywhere. There's no break anywhere in the function, it just keeps on going. On the other hand, the other two functions, there's some sort of a break. There's like a little hole in the line at the top, and there's two asymptotes where you like jump from one side to the other on the function at the bottom. If you have a function that just keeps on going and it has no breaks, we say that that function is continuous everywhere. Normally what you're looking at is something that's either a polynomial function or like a sine and cosine function, something that typically doesn't have any breaks no matter what you do. The function you're looking at here, where it's a line that has a hole in the middle of it, this has what we call a removable discontinuity. That basically just means a hole in the function. It's called removable because I could get rid of the discontinuity by just filling in the hole. And if you do that, it would just be a normal line. So if I said, where is this continuous? It's continuous everywhere left of that line and everywhere right of that line. So negative infinity to 2 and 2 to infinity. But there's this break in the function at 2. This happens when you have a function that if you wrote the equation, it's a fraction, and this would have like x minus 2 on the bottom of the fraction. It would be undefined at that one point, but everywhere else you could plug it in and it would work out fine. Your book mentions the term jump continuity, and the function you're looking at here has what we call a jump continuity. If you look at A, just left of the y-axis there, you can see you jump from the x-axis up to the top there. There's this break in the function. Again, it's continuous on the left, and it's continuous on the right, but you can't get from here to there in the middle. So there's a discontinuity. Much more common than that is something like this one, which happens to be a graph of a hyperbola that you would have done in trig class last spring. And this function has what your book calls an infinite discontinuity. That basically means it has an asymptote, a place where it's undefined and the graph goes up to the top and down to the bottom. It goes to infinity. So, when you have something like that with asymptotes, that's called an infinite discontinuity. You'll see some questions where they'll ask you, where is this function discontinuous and what kind of discontinuity is it? And again, if there's a hole in it, that's removable. If you've got a break, that's a jump discontinuity. And if you go up to the top or down to the bottom, that's an infinite discontinuity. Pretty much always when you're asked to look at discontinuities in this class, you're going to be just looking at a graph and figuring out what's going on with it. But again, the way that happens is you have fractions that are undefined. The function you're looking at here will have some sort of discontinuity at 7 and at -3. And we'll talk later on in the year about just why that is and how it works. Another thing we're going to ask you to look at graphs and see if you can figure out are the terms increasing and decreasing, which are basically kind of common sense terms. Increasing just means the graph's going up as you go from left to right. Decreasing means the graph's going down as you go from left to right. So hopefully it makes sense that the function on the left is increasing and the function on the right is decreasing. If you have a function that's not increasing and it's not decreasing, we call that constant, which just means, of course, it would be like a horizontal line. And the one on the right, hopefully it makes sense that it's decreasing on the left side until you get to -2. It's constant in the middle between -2 and 2, and it's increasing on the right. And finally, another thing we want you to be able to find from graphs are maximum and minimum values, which basically means just where on the graph are you at the highest or lowest point, either for the entire graph or for a part of the graph. So like on the graph you're looking at on the left, hopefully it makes sense that the minimum point of this graph is at the point -2, 0. That's the lowest this graph ever goes. It's never going to go below that. On the right-hand side, there is no absolute maximum or minimum. However, on that part that's in the middle of the graph, I could say that the origin, 0, 0, is a maximum point for that part of the graph. Again, it's just the highest or lowest for the part of the graph you're looking at. Well, mostly when we talk about maximum and minimum points, we're going to be looking at graphs. Sometimes you can also see information that's presented in a table and scan through it and figure out where you might have a maximum or minimum. On the one you're looking at here, if you just look through those numbers pretty quickly, hopefully you could figure out that the point 2, 0 is going to be a minimum point, because both when I go through 1 and 0 and -1, the numbers keep getting bigger that way, and when I go through 3, 4, 5, the numbers get bigger the other way. So 2, 0 is like the absolute bottom of this. And in fact, if you were to graph this function, what it's going to end up being is a parabola where the bottom of it is at the point 2, 0. The very last term that comes up in this section of your book is the term bounded. And basically, what bounded means is that the whole function is either above or below some number. If you look at these graphs that you're shown, these are straight out of your book. The one on the left, it tells you is bounded below. That means that whole graph is above some negative number. We don't know what that is because there's no markings on here, but every part of the graph is above where that minimum value is. The middle one is bounded above because that whole M shape is below some positive number. And the third one is bounded both above and below because the entire graph is between like maybe -1 and 3. It's between some negative number and some bigger positive number. So bounded just means that everything on the graph is above or below some point. And so again, today you want to think through the terms that we've done, figure out how you can find domain and range with graphs. Are graphs increasing or decreasing? Where are the maximum and minimum values? And are they bounded? And you're going to be doing some problems next week that will get you started working with that. And then we'll go on and learn more about functions after that.